Yeah, hi, Miji from the future here. The audio in the latter half of this video is kind of scuffed, so I'd like to apologize beforehand. I didn't have enough time to re-record all of them, so sorry about that. I will try to re-upload the video at a future time. Until then, please do feel free to let me know if there's some parts that you can't really understand. I'll try my best to explain it down in the comments below. Enjoy the video. Minus b plus minus square root of b squared minus 4ac by 2a. Probably one of the most infamous lines you'll ever learn in school. Right after mitochondria is the powerhouse of the cell, and right above every action has an equal and opposite reaction. Now you probably know this as the general formula to solve any quadratic equation. Here you have a general form of a quadratic equation. Grab the coefficients, plug them into the formula, and boom, you have your two roots. But what about cubic or quartic? Do they have a general formula? Nope, absolutely not. Wait, no, get out of here. You don't exist. So yeah, anyways, like I was saying, there is no general formula to solve absolutely any polynomial. However, what we can do is find certain relationships between the roots of polynomials to figure out something useful, depending on the situation, of course. Let's just show you what I mean. Normally, when you have a quadratic equation like this, you would factorize it a step at a time and end up with a line like this, regardless of what technique you use. Now, I know, you also probably encountered lines like this or like this, but none of that really matters because they're just different representations of the same thing. So all in all, you can represent absolutely any kind of roots in this form. Whatever the case, to derive the types of relationships I'm talking about, we'll actually need to start from our last line and work our way up to the top. For the sake of the topic at hand, I'm gonna rewrite the two roots as alpha and beta. Multiply the two, bam, you get this. Group them together, boom, you will get this. But now look, uh-oh, we didn't get the first line yet. No problem. Just divide the first line with a, and now we have something we can work with. If you take a look at the second and third terms for both the equations, you'll notice that they correspond to each other. You can quickly figure out that b by a is equal to minus alpha plus beta, which you can rewrite as alpha plus beta being equal to minus b by a, and c by a equals alpha times beta. Now hold on a second. You might be tempted to solve these two equations simultaneously to figure out some kind of generalized solution to the roots. But no, actually, if you do try to solve this, you'll actually end up with the same polynomial, just in terms of beta instead. So no, tough luck, you can't solve this. So now what? Big deal. I know that the sum of the roots is minus b by a and the product of the roots is c by a. How does that help me if I can't even solve the actual roots? Aha, but here's the thing. That's the point. The goal here isn't to find the roots necessarily, but to figure out other aspects of polynomials. If you were simply given the roots, you would be able to derive the original polynomial by a whole bunch of multiplications as previously seen. But if you were given the sum and the products instead, you would be easily able to figure out the polynomial in a single glance. And this actually applies to all the higher polynomials, albeit a bit more complex. Which is a great time to introduce you to our first set of notations. The sum of the roots as sum of alpha, and the product of the roots as sum of alpha beta. Now hold on a second. Did you just say sum of alpha beta? As a matter of fact, I did. To be more accurate, it should actually be the sum of paired products of roots. Things will be much clearer when we move on to cubic equations. But before that, I'd like to provide an example for quadratic equations. Suppose we've been given the equation x squared plus p minus 5 times x plus p equals 0. P has to be a integer value, and we've also been given that one of the roots is twice as large as the other root. Firstly, we establish the sum of alpha as minus b by a and the sum of alpha beta as c by a. We then substitute a, b, and c with the respective coefficients and expand the sums as their respective alpha beta expressions. Finally, we substitute one of the roots as being twice as big as the other root, which leads to a simplification like this. Resolving further, you end up with p being equal to these two values, So you ignore the one which is not an integer, with p being equal to 2 and your resulting polynomial being this. All right, all good. I'm gonna move on then. Okay, so now that we're here, let's start off with cubic equation. The same thing applies. You have your general form of the cubic equation, you divide the entire thing with a, and you end up with, on the other hand, we have x minus alpha times x minus beta times x minus gamma equals 0. If you multiply the first two, you end up with our original quadratic times x minus gamma equals 0. Multiply the first part with x, you get this. Multiply the first part with minus gamma, you end up with this. And finally, if you group them together according to their respective powers, you end up with this. Now, straight away, right off the bat, you'll notice that the sum of the roots is still minus b by a. But when it comes to c by a, instead of having just the product of the roots, you actually have the sum of the product of roots. To be more precise, it's the paired product of roots, because right in the next term, we have the product of all three roots together. You see what I mean? So essentially, if we were to use the notation that we learned before, the first one would be sum of alpha, which is the sum of the roots. The second one would be sum of alpha beta, which is the sum of paired products of roots. And finally, we have sum of alpha beta gamma, which would be the sum of what's pairs but three? Triplets? No, that would be twins. Pair but three. Yeah, triad. Let's go with that. So the sum of triad products would be minus d by a. So to quickly summarize this video, we have quadratic equations, the sum of the roots of quadratic equation, the sum of the paired products of quadratic equations, the same things for cubic equations, and also the sum of the triad products. Now you might be asking, wait, is that it? Do we just keep going further to quartic equations and pentic equations? Well, yes and no. Although you can use these formulae to figure out a polynomial itself at a glance, that's not what this chapter is about. Using these formulae, we can actually derive several other different relationships across different kinds of polynomials, which we'll be learning in the next video. Stay tuned and take care.